Recording. Okay, so I suppose a lot of you would know. Can someone say how to do this? We will just do this quickly. So how many zeros are there at the end of this number? This is what we're interested in. So this is a factorial, but it is in a slightly, so we don't want to find value of 5 to the power 12 before actually finding the number of zeros. Right? So how many zeros would be there? Okay, no, what should be the method behind this? Like, how should we approach this? The actual answer I don't know myself. What should be the method? So, yes, please. Yes, right. Then you get it. Yeah, absolutely. I think that's what Aditya also said. That's right. That's exactly what we have to do. So the only chances that we may get, oh, this is 5 to the power 12, what to do? Yeah. So that is the problem. But the thing is that we do not have to expand it, okay, as we see. So let us just run through it. This is just something that, we know, but still highest power of 10 in 5 to the power 12 factorial. This is what the question is. This is exactly what the question is, okay? But then this is the same as the highest power or the maximum power, okay, of 5 in 5 to the 12, okay? Why? Because obviously we explained it in detail, but it's very easy to see because simply put, because there are more fives, sorry, there are more twos than fives, right? There are plenty of twos available, right? If you expand this number, there will obviously be more twos as factors than fives. So we can just look at the highest power of 5 in this number, right? And that is basically, in this number, right? In this number, so from 1 to 5 to the power 12, how many fives are there? You do this, obviously you take the floor, or, if you have explained it, just take the integer part. Yeah, and then so on, right? 5 to the power 12, but then numbers like 5 square, you would have to, yeah. So for those who have not seen, it's a good problem to just think about why this works. Okay, why am I doing this 5 square and 5? This is a good question to just think about, but nevertheless, it should be easy to check. And so on. It even becomes a very easy summation in the end. Yeah, it also becomes a very easy summation. So just work it out from here, okay? So it works because of the number 5, and that's why it works. Okay, that's why it becomes easy. Otherwise, it would be a little more tricky. Okay, so I think this was easy for all of us then. Yeah, so maybe I should just easy. So you have to find you should try to find the last answer. So you see, this is a very interesting sum. You can already feel that, right? It seems like a very interesting number. It's a big number, but it seems like a very interesting number. Obviously, some of you who have done it, so there is a formula for this, which you will study later on. But for time being, you just try to explore and see what it should be. Okay, just think, well, how can you add this number in a faster way? Just think. If you know the formula, it's very good, but if you don't know, then also it's better because you can just think about this. Okay, yeah. In any case, for now, you can just try. Otherwise, you can leave it. We'll do geometry progression then. But yeah, most of us. That's not the. Okay, try to see how you can add this. So what you can do maybe is just take small numbers and try and see some pattern and then see. Okay, but that's the summing part is not important. Okay, so this was a very simple question. Let's move to the next question. Yeah, this next question is what I'm interested in. Find the, so till now we have, so in the last class we saw number of zeros at the end of n factorial, that all of us know. But this is an interesting discrete question, is find the number of, this was also some contest question. Okay, I don't remember, the numbers were different and such, but I knew that it could be done in a good way. So because I'd seen it in some contest. Okay, find the number of, sorry, find the rightmost. Okay, find the rightmost non-zero. One second, sorry. Find the rightmost non-zero digit in 53 factorial. Okay. This is interesting question. So we know that 53 factorial ends with a lot of zeros, but how do we find the rightmost? So there'll be a lot of zeros. We can also find how many of them are there, but we're not interested in that. But then there will be something here which will be non-zero. Right? At some point, you will get a non-zero number, non-zero digit. What will that digit be? Yeah. What will that digit be? That's what we're interested in. So only Advita had sent the solution of this to me, but the technique there was more of a brute force. So I'll not discuss that technique here. I'll see if some other people have tried with some other techniques, and then I will suggest the technique I have in mind. Okay. Yeah. So let's think about this. So has anybody thought about this? Okay. Okay. Let's see. So can we multiply the? Yes. So that is what we are trying to do, right? Okay. So from what you have said, the problem does simplify to something like this, right? 53 factorial we know is, as you have said, is one, and as we know this one. So first of all, just the definition, yeah, goes like this. The interesting thing about this question is there are many ways to do this. One is quite brute force, brute force, and not complete brute force, but not actually finding the value of cos, but some sort of prime factorization and such. But yeah, so first we write this. simplification. Then, so what one of his question is saying, what we can do here is we can automatically make a simplification. Yeah, and that seems to be that 1 minute. So you want the, yeah, is that since you're only interested in the non-zero digit, okay, since we are only interested in the last non-zero digit, so this, or I should rather say that the last non-zero digit of 53 factorial, yeah, this of this thing, right, would be equal to, we can just, maybe this is correct, we can just do this. We can go till 9, okay, and then what's next? Maybe we write a 10, but then instead of this 11, we can just write a 1, and instead of the 12, we can just write 2. Do you think that is correct to do? Instead of 13, we can just write 3. Yeah, yeah. So this, well, this does look correct, but I am not completely confident about this. Is everybody convinced that this, it's okay to find the last? So then what are you going to do with the 20? Are you going to write it as 10 or what? 10 into 2, what are you going to do? So this is, there's a question mark. What do people think? Do you think this is correct to just take the last digits of all of this of each of these, of each of the factors? Is it correct to do that? Except for the multiples of? Yeah, yes, we have to be careful about that. Exactly. That is my point, right? That you have to be careful about that, okay? Because see, the problem is that if you were only looking for the last digit of a number, okay, if you are only looking for the last digit, this is a different problem. This is not just the last digit, okay? This is the last non-zero digit, okay? So if you are going to, if you're going to skip this 20 and you're going to call it, I don't know what you're going to call it, you're going to call it 10, then that's not correct. See, calling 12 as 2 is a problematic here, right? Because 12 has more powers of 2. And so that might, obviously the last digit will not change if we do this. The last digit will not change, but the last non-zero digit can change. Okay, so it's a one has to be careful. Yeah. So the question is, what changes do we make to make sure that the last non-zero digit does not change? Okay, so what we have to be careful about is last non-zero digit shouldn't change. Okay, so once again, I mean, here then you can say that, well, those factors which are not contributing, so you can say that those factors which are not contributing to 5, sorry, yeah, those factors which are not contributing to 5, those you can, for those numbers, you can only take the last digit. But even that is not completely correct, I think, right? Because even 2 has a role in it. So there are a lot of things that one has to be careful about, okay? But here is what you can surely do. If you take from, let's just think about things from 1 to 10, okay? From 1 to 10, how are you going to get the zeros? Okay, from 1 to 10, how do we get the zeros? Obviously 10 is already there, and then there is 2 and 5. So we can just, you know, take that out separately, 2 and 5, and then obviously 10 is there. And apart from this, we can, these we can safely keep 3, 4, 5, 6, because so those which are contributing to the last, sorry, those which are contributing to zeros, we are keeping them separately. Okay, this 4, sorry, that's wrong. Yeah. No, they are not right. Sorry. Yeah, this 4 is not contributing. Okay, in this 6, the 2 is not contributing because they've already paired up. Okay, so these are the things that one has to be careful about. Okay, but still there will be a pattern after this grouping. Obviously, all this can be simplified by using some modular arithmetic. Okay, but if you just use the rules of modular arithmetic, then you may not know what you're actually doing. You're just following some rules maybe, and then you have to prove those rules and so on. So it's better to do some problems like this for some time, and then you can appreciate the rules and see that, okay, is this the language that we use to simplify and so on. A lot of things that we do again and again, and so on and so on. So that's why let's just do it like this first. Okay, and yeah, obviously, and 3, 4, 6, and then we have obviously 7, we have 8, and we have 9. These things are not contributing. Okay, so this is how we will go. Okay, and even here you see from, so what should we do with this 11 to 20? Any ideas? How should we, rewrite it so that the last non-zero digit is not affected, and so that it has some resemblance with this group, right? Then only it will be useful. Yeah. Okay. So you're saying that you can take the 12 separate out and the 15. Yes. Yeah. Right. Yes. So you can take the 12 out. Yeah. So then this does become clumsy. Can we do better? Yeah. But then what else can we do? Yeah. So we have to do this 12 and 15 if we take out separately and this. But yeah, again, we do save something, right? So this 11 again is just a 1, so we did not write it. And then we have the 13. The 13 I'm writing as 3. Is that okay with everyone? And the 14 I'm just writing as 4. Okay. And similarly 16, 17, 18, and 19. Now, this may not again be the best way to do this problem. Okay. You guys can think about more better ways. Okay. But certainly this is slightly better than doing the prime factorization, and which is also not hard because we have the formula and so on. But in any case, we have this. Okay. And you see, so in this way, you can continue. Okay. In this way, you can make your groups. Okay. So what will happen is that what is advantage of this method is that, see, these groups are fairly similar, right? These groups are similar. And you will get, so I'm not completing the problem. Okay. Let's try to complete it from here. And along these lines. The good thing about this method is that these groups will keep appearing. Okay. And well, are there any better methods? So if we keep the 2 minute. Yeah. So, I mean, this group, you can certainly calculate the last digit. So what will it be? So we have 3, 4. So we have 3, 4. So the 6 you can do it directly, but the 6 you can write as -4 and -3, and you can just calculate directly also. Okay, I'm just doing this for speed. -1. So 12, and then so that's 2. That's 2. That's 2, and that's 2. So this is 8. Okay, so you see this is just 8. So then you will get these 8s again and again, and those you can isolate. Okay, so you will get 8 to the power something, and its last digit you have to find. Okay, along with, obviously, from here also, when you extract the 2s and the 5s, you will get the other parts, right? Those last digits also you have to, but there will be a pattern in them also if you keep doing it. Okay, so yeah, this is my idea. Okay, this is slightly better because we get these groups of 8s. Yeah, so just take a minute and see if this is all clear, and I'll just think if we can further make this faster. So this will be obviously continued. Yes, in fact, there is a faster way, but that will involve some new notations, okay, about negative powers of numbers and their, last digit, their last digits. So that is a little, will be slightly new. So let me see. So I don't think I can say it in elementary language right now. So what is the idea here is that you do, no, that will not work. The last digit will not change, but since it's not the last digit, right? So yeah, 53 factorial. So this will be, so this number is, so let's say at the end of 53 factorial, there are, I don't know how many zeros are there. Let's say there are x zeros. Okay, x zeros. The method we saw is already much better, because if it's 100 factorial also, you can make those groups and that will help you, okay? But still, I'm just contemplating if I can do a little faster. Let's say there are x zeros at the end of 53 factorial. This is very easy to find. I'm sure all of you can find this. Let's say there are x zeros, okay? Then the number that we are really looking at, whose last digit we want to find, is this. Yeah. Do all of us agree that we're basically trying to find the last digit of this number? Right? Yeah. So we're just trying to find the last digit of this number, and yes. So yeah. Now yeah. So from here there are good methods to do this, I think. So we are trying to see if this is how much remainder does this leave when you divide by 10. But it will be difficult to say it in elementary language. Yeah. Yes. So we will not try to make it so fast right now. Okay. For right now, let grouping is good. And if you can think of better ways to group, better. Okay. So this was some, I think, AIME question, though the numbers were different and it was in a more complicated way they had said. Okay. Oh, sure. So that's right. Yeah. So you see, when you group, right, then you understand that each of these groups, you get 8s, right? Each of this group, you get 8, right? So 8, and so these big groups. So how many of these groups will be there? 4 groups, right? So you will get 8 to the power 4 from the big groups. And it is fairly easy to find the last digit of this. You can just write it as 2 to the power 12 and just do and see a pattern, 2 square 2 cube, and just see a pattern and do. Okay, so that part is done. And then what you do is, see, these are just 0. These we are not interested in, because they will just give you 0. And similarly, but from here you would have to take away the thing. So you will have 6 into 2 into 5 into 3 into 2 into 10. Okay, so then this and this, they are just 10, so they are out. And then you have 6 into 6. So you have 6 into 6 here. And similarly, when you look at the next one, where you will have, wait, so what will be the next one? Yeah, you'll have 20, not 21. So you have 25. Okay, so you'll have 25 and you'll have 30, right? And then for 25, you need the two, you need 2 2s, right? So you'll have to take some, maybe you take 22 or you take 24. Okay, let's just take 22. Okay, so then from here you can again see the zeros, right? You'll get this, and then obviously you'll have 21 factorial, 21, 22, and so on, which will be 1. 22 is gone, so 3, 24, 26, 27. So once again, you'll get the same group which you have already taken here, right? And from here again, you can just take out the you can take out the 2s and the 5s. Okay, Yeah, but here again, you will have slightly right, because there are is 25 is here, right? So you can just give it an extra 2. You can just so this group will be slightly different because of the 25. Is that right? Yeah, this group will be slightly different, so you will have to just do that. I don't think you can do anything with that. Okay, so here we will have to give 24. Again, if you want to do it in the elementary, otherwise we can use inverses. But yeah, so you will have the 1 and the 2 and the 3, 22 ka 2, and 24 we will keep. Okay, so again, for this group, you will have to do. This group will not give you 8, it will give you 4. Okay, so you were getting 8. Yeah, so that's like mistake. Yeah, so this was giving you 8, this was giving you 8, but the next one will give you 4. And again, you can continue like this. Is it okay now? Then for the 40, that group you can just do. That group will be simple, right? Because 40 you can keep, and 45, and then 42. That's it. And then 43 you can just write 3, because they are not needed to get the tens in the end, right? 3, 4, and then you have 6 and 7. So this will again just give you 8. So you'll have 8 cubed times 4. And the last digit of that is very, very simple to find. Okay. And then from here, again, you can extract the 10 and you can get the small number whose last digit you can also find. And if if it was a bigger problem, you could continue like this. 25 group is the only problem. Other than that, 25 doesn't come till 100. Okay. So it is still slightly ad hoc, but okay. Yeah, this is how it is. Is it okay now? Yeah, okay, but just work out the details. Okay, you will have to work it out. It's not be a very small, it will take some time. Maybe it's going to computational by nature. Okay, so let's come to the which one do I want to do next? 1 minute. 1 second. Yeah, let us just do this again. This is slightly easy, I think. So this is find the last two, just the last 2 digits. So this time it is last 2 digits, not last 2 non-zeros, last 2 digits of 1 factorial plus 2 factorial, and so on. And so on till 100 factorial. Yeah. So yeah. How do we do this question? I think those who had submitted, I think they just computed the last digit. I wanted the last 2 digits. Okay, how do you get 53? No, at least 1 0. But is that sufficient? No, I mean, that should not be sufficient, right? But you have the idea. Okay, so see, the idea, this is very simple. The idea of this problem is very simple. Okay, again, these are usually just MCQs. Okay, these are not very simple, but yes, absolutely, that still 9 factorial you have to do. That's right. So the simple idea is that yeah, is that after some time, so after some point, or that people have already said, but abstractly, after some point, there are or rather I should say after some point, each factorial, okay, ends, so each factorial ends with at least 2 zeros. Yeah, ends with at least 2 zeros. This is the thing, and that you should just figure out. Okay, it's very easy because 10 factorial obviously has 2 zeros. Okay, and so beyond this, you need not worry because they will just be numbers that are ending with 2 zeros at least. Okay, so they will not contribute to 10 factorial. Is that sorry? They will not contribute to the last 2 digits. Is that clear to everyone? Okay, no contribution. That's all. Now you have to just, now this is easy. You can do from 1 to 9 factorial. Okay, again, you can try to try to do this faster, do this, okay, but just do it anyhow. So yeah, that's also simple. Any doubts with this? Okay, okay, so let's move on. Yeah, so here is a slight variation. So P is product of first 100 odd integers. Yeah, P is a product of first 100 odd integers. So now the numbers are not factorials. I think Soumyadeep had asked this question last time. What happens if what happens if the product is not of consecutive numbers, meaning that it's not, doesn't form a factorial? Then how do we do it? Okay, so that's what this question is here, and let's see. This is just, it's obviously not an arbitrary product. 100 positive odd integers. Find the largest power of 3. Okay, find the largest power of 3 that divides P. Okay, yeah. Let's see how we can do this. Yes, yeah, please. So yeah, so what will be? Yes, you can do that, or yeah, or you can just see the this is the pattern, right? So it will be 2 times 99 plus 1. Yeah, because the first one is 2 times 0 plus 1 and so on. So that's very easy. So this should be clear to everyone first. Yeah, this is what the last thing is. Okay, so this is 199. Yes, please go on. Yeah. Odd multiples of 3. Okay, go on. Yeah. So what is the last number that's a multiple of 3? That's 198, right? So 198 is 3 times 66. Yes. Okay. Ah, okay, okay, okay. Okay, let's see. No, but the little problem is that some of them, okay, so let me just say what you've said more clearly, more explicitly, and then we can see if there is some issue with that. Okay. So if we just write this out clearly, we go on till 198 times 199. So the idea that has been suggested is that you need to take, or rather just compare this. That's what basically it's being done. Just compare this with the full factorial. Oh, sorry. Yeah, 198 will not be in this one. Yeah. Sorry, not in this one. That's right. Yeah. But it was not needed. I had written it wrong. Yeah. So we'll have 197 and then 198 and then 199. So we're just comparing it with this. Now let's compare. So what has been suggested is that here you find out the numbers that are multiples of 3. Okay. And that's very simple to find. How many numbers are multiples of 3? So let me write that. And then we can clearly see if there is any problem or not. How many numbers are multiples of 3 in the latter one, right? And so that's not hard to find because you have 3 into 1, 3 into 2, 3 into 3, and it goes on till 3 into 66. Okay, so there are 66. Okay, and then so the thing is that then what is being suggested is that by symmetry, 33 should be the answer. Have I got this right? Is this what you meant? Yes, that is right. So does everybody see that this is not done, right? This is only finding the number of multiples of 3. So that is 66 of them. If you look at from total thing from 1 to 99, 1 to 199, but then by symmetry, half of them are odd and half of them are even. Okay, but yeah, so one can continue like this. Okay, now you can go for the 9s. Okay, then you can go for the 27 and you can continue like that. And again, maybe by symmetry you can say, but sometimes you will not be able to use symmetry. I mean, sometimes there will be a slight problem, right? Because let's say this was 65. Then you have to decide, so then one more than half of them would be odd. Okay, so that is certainly a way. Okay, let's just execute one more step of that. Okay, and then we can see. But I would like to also think if there is a better way. Okay. Well, it is essentially the same because what we are doing essentially be the same, but we'll see if we can do it. So this is the thing, and see this number of multiples of 3. This could also have been found directly by 199 divided by 3. Right? That's what we basically did. Yeah, those 2, and then divided by 2 because by symmetry. So this, let's write this clearly so we have space for the next one. So this is 33, 66. Okay, so P has 33 multiples of 3. Okay, so we have found how many numbers are there in P in our product, which are multiples of 3. Okay, now we need to find the multiples of 9. Okay, so how many multiples of 9? So let me just call this S. Okay, or it's just 199 factorial. How many multiples of 9 in 199 factorial? Okay. Now again, you see this, you can just find, we already know this is how the formula was made, right? Number of numbers which are multiples of 9, multiples of 27, and so on. So obviously this is the formula. Then 9 to the 18, 1, 9 to the 18, 1. So it's 22. Okay. So in this, right? So in P, how many are there? We have 11. Once again, just in the same way, right? Multiples of 9. Is this okay with everyone? Just by symmetry, right? It should be half, clearly. Is that clear with everyone? Okay, because you can just write this very explicitly and think about it. You have 9 into 1, 9 into 2, 9 into 3, until 9 into 22. But you see, this is not taken in P. 9 into 4 will not be taken, 9 into 22 will not be taken, and so half of them we are going to take. Okay, and continue like this. Continue, and please continue and find the answer. Okay, because sometimes if you get an odd number, then you have to think. I'll not say what to do, just think. So can we all finish it from, try to do it from here? Okay. All right, please try to do it from here, because I'm not completing them, because then you will not do anything. In the sense, okay. Let's just also try to see if we can do it faster. Is there an alternative way? If I will not say faster, but is there an alternative way? Because why I'm saying this, because this number is combinatorially very, very useful. Okay, just you will see it will arise. Okay, so in fact, what happened is that in one of our one of our end semester exams, okay, there are 3 questions. Okay, so there are obviously 7, 8 questions. So this course in enumerative combinatorics, there were around 8 questions, 7 questions, something like that. It's an end sem exam. 3 questions had this as the answer. 3 very different looking questions. Okay, so there were 3 problems. Okay, maybe at some point one of them I can discuss with all of you. Other 2 will take some time, some complicated things. But as I'm saying, 3 of them had this as the answer. 3 very different looking questions. Okay, one was some graph theory related counting question. One was some arrangement question, and the other was some other, okay, some permutation block partition kind of question. So, but yeah, so that's why this number is very significant, and it's also not, we don't pay that much attention to it. Okay, and also the questions whose answers is not very straightforward. If the answer was n factorial or 2n plus 1 factorial, then usually the problem is easier because we know this number a lot. But if the answer is this, okay, this is also denoted as, so maybe some of you know this. I didn't discuss this because too many notations not useful. It's also called double factorial. They have actually give a notation to this because if it pops up, especially later on. Right now, it will not pop up so much. Okay, this is not the same as this, obviously. Okay, this is just a symbol. This is just a symbol for this thing. Okay, but this is obviously, you can understand, this is 199 factorial, a huge number, and its factorial you take again. So they are different things, obviously. Okay, now one can ask questions, but it's very, so these numbers are very interesting numbers out of questions. Okay, let's try to think if we can do this in a different way. Okay, so alternate, any alternate. Because if others have tried it, have they tried it in any different? I'm just wondering because this number pops up in so many ways, and so maybe there's. So what I had in mind, so I myself not very sure, but I think there is a way which is which will make this problem exactly like a factorial problem. Okay, right now we had to kind of had to take some cases, and sometimes there will be some differences. Okay, especially if the number of multiples of, let's say, 27 turns out to be an odd number, then you would have to make a decision and so on. So it's not very formalized. You can still obviously break it down and write an algorithm, but yeah, if we can manipulate this expression. So the idea I had in mind, if we can, and this is a problem on its own, just an identity that we'll get. Can we manipulate the expression, or basically what I'm trying to say more specifically is write it in terms of factorials. And this is really what we also want to learn, right? Is how can you take expressions and write them in terms of factorials and or combinations, binomial coefficients, which we'll see in details. Okay, write in terms of factorials. Some of you may have seen this. This is a standard question to write this in terms of factorials. Those who have seen it. Others, you can just think about this. Write it in terms of factorials. It's always a good habit to try to do this. A lot of binomial coefficients thing is just about rewriting that expression and just doing the summation. Okay, we'll see. Okay. Right. So let me do what you have said. Yeah, I think that's the idea. So first we have just again, writing it. So first we have this all the way, and then very simple idea. You just, okay, so I've created, so I should have right to the right, but in any case, yeah, it will going to look bad, but yeah, anyways, we have this, and then is 6, and is 8, 12. So you just multiply, divide by this thing. Okay, just the missing things. Right, this will work. That's nice. Very nice. Okay, this is okay. And then from here, as I think Orko has said, we have 199 factorial, and then the denominator. Okay, can anybody else say what we should do with the denominator? Orko, you don't say, I think, about it. Anyone else can say, what should we do with the denominator? The numerator is already there. That's right. Absolutely. Yes, right. So but we will only take 1 2 from each. Okay, we will not extract all the 2s. No, not 198. Not 198. It will be 2. It will. There are. Yeah, that's right. Yes, yeah, absolutely. Okay. Please work out. Don't just believe me. For those who can't see it immediately, just work it out. Okay. Okay, do this. Work it out. You get this, and now you can just do the problem. Just find the power of 3 in this using the formula, and then you can just forget about the 2. So okay, let me not do all the scratching here. Okay, this is what the expression is. Yeah, this is what the expression is. Again, maybe not now, but we will soon ask for if we can do this combinatorially. Okay, we have done it using algebra. There is tremendously more merit in doing it combinatorially. Okay, but right now this is correct. Okay, now problem becomes very simple. Yeah, it becomes more like previous questions, right? You want to find the power of 3 in this. Just very simple, but just saying, you can just forget about this. If you want to find the power of 3, just find the power of 3 in this, find the power of 3 in this, and then subtract them. Simple. Now it will not be half. Okay, don't think it will be half. May not be. No, no, why not? So we are just taking a 2 from each term, right? Because there are 99 terms, right? No. How many terms are there? Are there 100 terms? So we have 2, 4, 6. So we have 2 into 1. No, yeah, that's right. There are 99 terms. Yeah, because there are 99 terms, right? And we are taking a 2 from each, right? 99 terms. We have 99 terms. We take a 2 from each. So you write it as, we are not, so that's what I was saying. We are not pulling out all the, we're not extracting all the 2's, okay? We just want to write it in terms, here the goal is slightly different. We want to write it in terms of factorial, right? In this way. And then you take out the 2's and you get 1 into 2. So you get 1, this becomes 1. So you get 2 into, wait, what have I done? Yeah, but I've made some, yeah, right? We get 2 into 3 into 4 into 5, right? We do this, okay. Yeah, right? And we get 99. Yeah, but just also work it out. Okay, so this is a very interesting identity. Okay. Is it clear with everyone? Please say, because because some of you may have not done enough algebra. So okay, all right, it's good. It's easy. All of this is easy, but just interesting ways to do the same thing. Now, the very interesting way, which I don't expect people to be able to do it. Last time also asked a question like this is, can you think of a combinatorial question? So let me first write the general expression. Okay, so the general expression here is that you have the numbers from, so here we have 1 to 5 till, let's say 2n plus 1. So we have, so this is, so this is n plus 1. So this is n plus 1 at odd number, but in any case. And this, so we now understand that you can write this as this times 2 to the power n times n factorial. Okay, this is what we have. This is what we have just, no, this is wrong, right? No, wait, this is right. Yes, this is right. Okay, but this is what we just did. Okay, it's the same thing, just replacing it by n. You can think of it in either way you want. Okay, now you see this equality we have established by manipulations. Okay, because we could use a lot of arithmetic. Okay, so we used a lot of arithmetic. We use the operations of dividing and so on. Okay, but the question doesn't really have, I mean, the question, to frame this question, you do not really need division or subtraction and powers and those order and all which we have used in this to do the problem, right? So the way the question is can be written, especially this can be written even without division, right? Can be written completely like with very minimal number of operations, just like this. Yeah, so this question can be written in very minimal language, just simply put. Yeah, but we have used a lot more things to do it, right? We just use the more structure of the thing to do the problem. Can we use less structure? Can we not use arithmetic and still do this question? Okay, so can we give a arithmetic less proof? You can even just try to do it for this. Okay, so we do not want to do any divisions, we do not want to do any cancellations, and can you still do it? Okay, now why can this be useful? Might be difficult to understand now. Why would it be useful? But it's just fun, at least. But it's very, very useful. Okay, soon these multiplication may be replaced by some other operation, maybe some kind of some different some vector cross product, tensor, or some dimension of something or something. Okay, there, or maybe it will be replaced by some polynomial something. Okay, there you maybe cannot do all those things. Okay, but if you have this a different proof, a different explanation, then you can just use it there as well, and so on. But maybe, so that's probably, so just think of it as a fun challenge. Just think about an arithmetic less proof. So what is the idea behind such things is try to think of a problem, okay, which you can solve in two ways, right? You can solve it in one way and get this, so you can already think of the problem, and then solve the same problem, just the same problem, solve it in a different way and get this directly. Okay, just you can just think about it, but it's not maybe not going to be easy. Okay, I do not know of the head also. Okay, I have to think. Okay, obviously the problem is going to be, you know, taking 2n+1 people and arranging them. Maybe that's one way to, but that's maybe not decorated enough to do it in a different, interesting way. So maybe you have to think of a way. Okay, think of an interesting problem which has this as the answer, and then do it in a different way to get this as the answer. Okay, think about it. Okay, this is just open-ended. Yeah, this is very useful. Okay, the double counting, double summations, and all that. Fubini's theorem in integration, all of them are just swapping. Okay, the order in which you are just doing the same thing in two different ways is really what it's all about. Okay, so let me not do more problems from what I had sent last time. This time I just send this set to everyone so that you can all see. Okay, let me just do one other question, which I had also seen. This is a logic question, otherwise it will just be left out. So I don't want to write this question because this will get already, no, this will, yeah, I don't want to write it. It's very big. Just want to somehow share it. Yeah, I think I can share a tab, right? But then I will lose the screen. So then, yes, what I'll do is I'll just quickly mail it to everyone. So this is the question about species and things. Okay, so I'll just I'm not even able to arrange this in a good way. So I'm just sending this. So most of you will have it, I think, but I should have planned this earlier. 1 minute. Because I really want to get done with this. 1 minute. Wait. Wait, not working. Okay. Yeah, I've sent it. Just if you can check it now, just see. Okay. So you guys have got, so there is this problem, right? The world is divided into two species. Yes, yes, yes. I haven't got, okay, I sent a mail. There should be some other way, right? To do this, but I don't know. Yeah, yes, there is a thing in that, right? Yes, yes, yeah, yeah. Okay. So I think all of you have it then. I think others already had it, I think. Yeah, okay. So we have, so the idea is that, look, you have two species. So we want to do this problem. So we have two species, vampires and werewolves. Okay, I'll still just summarize the question. Yeah. Okay. This should be SPEICs, whatever, doesn't matter. We have two species, vampires and werewolves. Okay. So each species, okay, so 1 minute. Each species, okay, tells the truth when talking about, so this is important, talking to and talking about the different things. Obviously, when talking about a species of its kind, okay, else it lies, and that's important, okay, else it lies. This is really what the content of the intro problem is, the details. Okay, every species, so suppose a vampire is talking about a vampire, then he will tell the truth, it will tell the truth, otherwise he will lie. Okay, and similarly for werewolf. Okay, that's really what it is. Now let us just do this part by part. I think it's maybe simple for some of us. Anyone has problems understanding the question, especially those who are just seeing it for the first time? Yes. So the questions I'll get into, but this is the situation. This is the scenario, right? So there are two species in the world, only two, and if a species talks about another species to some species, that doesn't matter. Then he will tell the truth if he's talking about a species of its kind. Okay, if he's making a statement about a species of its kind, else it will lie. Okay, this is just the thing. This is just the scenario. Let's just do the first question. Okay, I understand. So the part one. Okay, let's just write this. So Azrael says, it will be more clear once we just do this part. Okay, Azrael says Pila is a werewolf. I think we had already done this part, but yeah, I think that time we had just done it by, we didn't know, it just worked out. Okay, is a werewolf. Okay, so from here we need to show from just this statement, not, I won't even say statement, I will just say that this thing that Azrael says, yeah, this on a whole is a statement, right? Azrael says that Bila is a werewolf. Just from this, okay, show that Azrael must be a werewolf, right? This is, so can anybody explain how, those who have done this earlier, can explain how? Right. Yes. Right. You see, so it's a very simple thing, right? So if the statement is false, then it means that Bila is a vampire, and the statement is false means that Azrael is lying. Yeah. So Azrael is lying, and if Azrael is lying about, so Azrael is talking about Bila. This is what statement is. It's obviously there. Huh? Is what it is. Azrael is talking about Bila. Okay, and he's lying, and Bila is a vampire. And so obviously that means that if he's lying, then he cannot be lying if he if he was a vampire, then he cannot be lying when talking about a vampire, right? So it means that Azrael is a werewolf. Okay, so and in similarly that part is already clear. Okay. So this is a simple, does everybody understand the explanation? Okay, And you can, it's just that if you divide this into two things, truth, and obviously this can be done more formally later on into logic gates or truth tables and so on. But yeah, for now, this is manageable without that. Okay. Just you have to break it into two parts, and then you have to just analyze the cases and so on patiently. That's all it is about. But it becomes interesting in the later part. Is anybody not clear about this? Then I will ask someone else to again explain this. Okay. Let me just write this one also. Let's write this part. Okay. If Azrael is telling the truth, then Bila is a werewolf. Is W. Let's just write this. W. And if Bila is a W, Azrael is talking about Bila and he's telling the truth. So he must also be, okay, Azrael is telling the truth. So yeah, so Azrael is, sorry, is a, so he's talking about a werewolf and he's telling the truth, so he's a werewolf. Okay, just deductions. Okay. Okay, so if it's clear with everyone, let's move on to the next part. But we must learn from what we have got from here, something interesting, right? See, we have got an interesting statement that if a species says that some species Y is something, then he is also that something. Okay, so if X says Y is a V, then that means, then we don't obviously know, we don't know about Y. We've already seen there are cases, but then X is a V. Okay, so a species will never, so basically intuitively it may, like wolves don't know other creatures. Let's say wolves don't know the word where foxes, let's say, I don't know, something like that. But they are from the same family, I think. But in case, this is what we learned from this. Okay. Now let's move to the second one. Okay. Because we'll have to, if we want to do the later ones without too much casework, then it's good to, learn what we can learn from this. Yeah. Let us do the next one. So once again, I think I've seen this. So here we have Caesar says, a minute. Caesar says Dita says Elith. Yeah, Elith is a vampire. Okay. So Caesar says that Dita says this. Okay. Once again, can someone explain what we can conclude from here? Hold on. Why? So from here, you're saying no. She's not. But we can't yet say that she's saying this. Caesar is saying that she's saying that. No, I think both of you are making the same mistake. Yeah, go on. Yes, yeah, that is the thing, right? So that's the mistake that has been made earlier, right? Let's see, we don't, this is not saying that Dita says this. No, we don't know that. Caesar is saying that. So we cannot rush to the conclusion just by applying number one. We cannot apply that because we do not yet know. Okay, so I think 1 minute. So before I go to Advita, I think there is one thing that has been claimed that if, so you are saying, Pragya, that if Caesar is a vampire, then you're saying Dita is a vampire? Can you explain? Hmm? Yeah. Okay. What if Caesar lied to Dita? Yes. In that case, we cannot say. Yeah. Okay. I'll let Pragya. Can you explain the false part? If Caesar is lying, Caesar is a vampire, but if Caesar is lying, Dita, that is tricky. I don't know. Huh? Oh, okay, okay. That I don't know. We can try that. We will try that maybe. Okay. Yeah. So you're from the innermost. Hmm, yeah. Huh. Yeah, but that will not take care of all the cases. Yes, there will be a lot of possible. Yes. 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 So that those cases you have to make, right? Otherwise, it's difficult. So I do not even think that this conclusion can be made, and obviously that initial conclusion also cannot be made. Yeah. So let's see what is being said now, right, Koshambi? So we will take this case, right? Caesar is either telling the truth. So let me just write it very clearly. Caesar is T, or Caesar is lying. Okay, go on. Mm-hmm. If Jita is telling the truth, then that implies yes. So if Jita is telling the truth, then wait. No, 1 minute. No, we don't even need that, right? Yeah, what you're saying is correct. But if Caesar says what you're saying is correct, but if Caesar is speaking the truth, okay, then we know that this statement is true. So everybody should pay attention. Here we can save a lot of work instead of taking 4 or maybe 8 cases, right? We can save some work here and yet be correct. Okay. Caesar says, Dita says Elith is a vampire. Okay, now if Caesar is speaking the truth, then this statement is correct. Okay, now see, try to understand this. This statement is correct does not mean that Dita is speaking the truth. No. Okay. No, no, no. We can, yeah. Yeah. So if Caesar is truthful, then we can, what I'm trying to say is that if Caesar is truthful, then we can immediately conclude that Dita is a vampire. We don't have to further take cases. Is that okay? Yes. Can anybody explain this? Or if Caesar is telling the truth? Hmm. Absolutely. So, Koshambi, right? Just in case in one, you can just do, right? Just replace Azrael by Dita, right? Just replace this by Elith and replace this by vampire. Yeah, we had proved that Azrael is a werewolf, and then in the same way you will get Dita as a vampire. Okay, so you see, it's the same thing, right? The moment Caesar is speaking the truth, the moment Caesar is speaking the truth, we know that Dita is a vampire. Sorry, we know that Dita says. So this means that Dita says Elith is a vampire. This statement. From this statement, you can say Dita is a vampire, right? Because if X says Y is a vampire, then X is a vampire, no matter who that X is and who that Y is. And even you can just do this for W also. Okay, is it clear now? This is the way you can save work. This is the way you can save work. This is important. Okay, and you can further iterate this and so on, but not for now, but guys who want can think about it already. Okay, so this is the thing. So this problem, see, the best way to do this problem is just to do it yourself. Just do the casework and do, because the way I will say or the way someone else will say, you may get more confused. Okay, but at least this idea, that's, you know, that that this from, you know, if someone says someone is a werewolf, then that person is a werewolf. We don't have to further take cases. These things are the ideas. Okay, obviously you, I will understand everything now, but also when you're doing it, just do it in your own way. Okay, so yeah, so let's just, so this case becomes very easy. This case is Theta is a vampire. Okay, but it's not done. So what can we conclude about Caesar? Can we conclude anything about Caesar? Caesar is what? Absolutely. Yeah. And again, just the same thing. Now we do not have to, now we're getting a hand on the problem, right? It's not just a truth table kind of thing. We just also understanding what's going on. Okay. So that case is done. So from there, we have Caesar as a vampire. What next? Okay, so let's write that. So then Dita says Elith is a werewolf. Okay. Yes. Yeah. So now you guys have got it. Okay, just work it out. Nice. So then Dita is a werewolf. Again, you're just applying that statement. The first thing, yeah, the kind of thing we prove first. Okay, and then from here, can anybody else who has not yet spoken in this problem, what can you conclude about Caesar from here? Okay, those who have already said I can understand, but Caesar is what? And with the explanation, of course. Take your time. Yes, I know you. Yeah, yeah. Yes, that's what it is. Okay. Okay, has everybody got it? Would anybody like to say it in a different way, maybe? Because I'm just looking for maybe someone can say it in a way that just strikes, that's just different and it's better than what we have said so far. So don't hold yourself back if you, okay, because we are interested. See, we are interested more in the ideas, okay, because we all want to do the math, we all want to work things out. Okay, so if you get these ideas, then you can build on that. Okay, a different way to say things and think about it, so that's why if you have a different way to say it, just say it. Okay, yeah, so from here it's as per guess said, so if Caesar is lying and Caesar is lying about werewolf, and Caesar cannot be a werewolf, cannot lie about, have to be faithful to the species. And so, yeah, that makes sense. So the Caesar must be a vampire. Okay. But here I was slightly confused here when I first had a look at this problem. Okay. By the way, I think the source of this problem, no, not I think, I know. I don't remember. So this is 2015, I know it is. So there's some college application. I forgot the name of the institute. I think Amanda, you would know. Do you know which institute? Which? Okay. So this is Oxford, for Oxford University. Okay. So this is easy. It's not difficult, but if we just work it out and do it. Yeah. Okay. Right. And yeah. So no. So what I was confused about is, see, if theta, if so, if you take the false of the statement, theta says Elith is a vampire. Okay. If this is false, so I'm just writing it like this way. If this is false, then that does not. So if you think of it very rigorously, right, or just truthfully, then that actually does not mean. So this should mean that theta, obviously that's what it is formally. Theta does not say Elith. Theta does not say Elith is a vampire. This is what the complement of the statement is, right? See, it is not necessary that theta has to talk about Elith. Or could there be a case in which theta does not talk about Elith at all? No, that would also but get us in a maybe a block, a roadblock. So what do you do with that? If theta does not talk about Elith, then in that situation, what can you conclude about Caesar? Maybe nothing. No, yes, Caesar. Yeah, but about Caesar. Yes. No, yes, that's right. So we can, obviously, that is already there. So if Caesar is lying about theta, then Caesar and theta are of opposite species. But then can we conclude that Caesar is a vampire? So yeah, because if theta does not say anything about Elith, then what happens? So this is where you have to really write clearly in the exam if it's a subjective question and tell them that, look, this is what I think. Because maybe they have missed out this case. I'm not 100% okay. So you have to just work it out. Or you could further think about this. I have thought about a few things from here, but just think about this. So maybe from here, theta does not say anything about Elith, then maybe you could make two cases. Okay, you could make a case in which Elith is a vampire. Okay, so you can make two cases from here. Elith is a vampire, and the second is Elith is a werewolf. And then maybe you could say, so I think that if theta does not say anything is leading us to a roadblock, then we can also say this, then you make theta and alith meet. Okay, you know, make them confront each other. And then there is a small statement here that says that each species is instantly recognizable to the other or something like that, right? They can recognize if what species the other kind is. That's obviously necessary for survival, so that is natural also, but it's there. And my point is that it is there in the question. Okay, then you can again make cases whether in this case if theta is telling the truth or not, maybe. But if you make all those 4 more cases, you will end up with the fact that Caesar is a vampire. Okay, but just work that out. Okay, just do this further thing. So this, and then if theta and alith meet and theta lies, then theta is a werewolf, and then Caesar becomes this, and so on, so on. Just see. Okay, just see what you get in the end. But this is just maybe I don't know if they meant to give this case or not. Okay, yeah. So if people can wait, I just want to complete the other 2 parts today, or at least the third one. The fourth one is similar. Okay, though we are out of time, but I just want to do it because we don't want to give this for the next day. Yeah, today we couldn't cover anything new, but as I've said, the plan, the next class, next Sunday, we'll partition it into 2 classes. And yeah, in any case, let's continue with this. Okay, I don't want to leave it like this. Okay. So let me remove all this now. It's already out of space. And let's try the third one. Statement. Wait, so where is the question? I've lost the question once again. What did it? 1 minute. Huh? I myself lost the question. We are, sorry. No, I found it. I found it. Yes, I found it. Yeah. So now the next part is that suppose there are n creatures. So now suppose there are n creatures. Let's just take, let's not take n for the timing. Let's just take there are 4 creatures. Because generalization is usually easy, but when I see the pattern, suppose there are 4 creatures on a table, circular table, sitting around. So let's draw it. Again, this will be easy, I think. We have to just do the casework, but we'll do it if there is something different. So there is 1, 2. Is there any clockwise? No, nothing. So 3, 3, 3, 4. Right. And then we have this. Each tells their right-hand neighbor, you lie about your right-hand neighbor. Okay, let's write it here. Each tells their right-hand neighbor, you lie about your right-hand neighbor, right? So for example, for 1, 2 is the right-hand neighbor. You can, if you want to do it the other way also, but yeah, if you look from their perspective, from perspective 1, 2 is the right-hand neighbor. So 1 will say to 2 that you lie about 3. Okay, so it's not telling him to do that. Obviously, this is just saying a statement. Okay, it may be true, maybe false. Yeah. What can we say about n? All right. So this is maybe we keep it n then. N, but we will obviously take small. We can also take small cases and see if for what it's working and so on. So yeah, the first thing that we want to understand is what can you say about n? What can we say about n? Maybe odd even kind of thing, right? Let's see. So has anybody tried this? Yeah. Uh-huh. Uh-huh. Hmm. Okay. Yeah. Right. 2 tells truth about 3. Oh, that's right. That's right. Yeah. So 3 lies about 4. Oh, so we can make all the conclusions once we start with this. Okay. Yeah. Okay. Hmm. Ah, yeah. Tells truth about 1. Uh-huh. So it works out. Huh. Okay. Okay. Yeah, and similarly you can, so let's not say this case explicitly. Yeah. So it will work out similarly. Yeah. That's right. So this is just a very straightforward reasoning, right? See the point, the idea, the thing, the main thing is that once you assume something about 1, it leads to this chain, it leads to this chain reaction, right? So you are able to make conclusions further and further. Okay. The other statements, who is telling the truth about the next one or not. Okay. So once you know the first one, you can just work it out from. That's all the idea is about. Now, let us just run this one once again. Okay. And the truth part I will not do. We'll just see. Okay. Let's just run this thing once again. Okay. So see, if one lies about, so if one lies, okay. So in this statement, I'll just want to share this in a slightly different way. Okay. In this statement, we replace, okay. What is happening is if one lies, then it means that one tells 2. Yeah, so this is, yeah, one tells 2 that you lie about 3. Okay. One tells 2 that you lie about 3. That's what it means if one lies. I mean, that's the first thing. But if one lies, it means that 2 does not lie about 3, but 2 tells the truth, right? So if 2 tells the truth about 3, it means that they are both of the same species. So if this was a vampire, for example, then this would also be a vampire. Okay. And obviously 1 is lying about 2 means that this was a different species. Is that okay with everyone? Yeah, this was a different species. Now, just the same. Yeah. Oh, yes, yes, yes. Yeah. Yeah. So the reason why it was working out, yes. So I think that is the most important thing. Yes. Yeah. So the reason why it's working out is because there are an even number of things. And we'll see it once again through this pattern also. Now once again, let's go now. So we know that 2 tells the truth about 3. That's the conclusion. Okay, because 1 was lying. Now, if 2 tells the truth about 3, let's see what 2 actually tells. Okay. So 2 tells 3. See, 2 is telling to 3 means that 2 is talking to 3, but at the same time, 2 is talking about 3. Is that clear to everyone? Yeah. 2 is also talking about 3. Okay, because he's saying to 3, but then he's also saying about 3. This is about 3. Okay. And okay, so 2 tells the truth. So it means that 3 actually lies about 4, which means they are of opposite species. And in this way, you can work out that 4 and 1 will be of the same species. Okay. And this will never work out if there was an odd number of things. Right. So suppose there was a 5 here. Right. We can see the pattern. The pattern is clear, right? It's going to be VV, then WW, and so on. Then this has to be W. Yeah. Let us actually do it. Let's actually do the next. You can see that it will not work out if this is not a number. Can anybody else try to say what we will get if the case, if it is 5? Let's say till here. Okay, we started with this assumption. Let's say we got till here. Now, what can we say about 5? Let's see. Absolutely. Right? So 3 and 4 are of different species, and 3 tells 4 you lie about 5, right? And that's a lie because there are different species. So this is a lie, which means that 4 actually tells the truth about 5. Okay, so it means that they are of the same. But then next step, when you do, you will get that 5 and 1 are going to be different species. And that's a contradiction, right? See, we started with W, we got a V. Next, we'll get a W, right? But then if you get this W, then this has to be a V because of just the circularity, right? Just continue like that, okay? So just work this out. That's this being W will imply that this will be a V, okay? And then that's a contradiction because we assumed that it is W. So it will never work, okay? So it will never work when n is odd, but it will work. Please write this out now, okay? Write this out, do all the cases, show it. Even for the truth, also write it out and just see. Okay? Please write it out, and if possible, also send it to me, okay? Then because unless you write it out in your own way, you will not know if you have missed anything. You may arrive at the same conclusion because it's already, you know it, but you have to work it out, okay? Yes, yes, no, I know you have submitted. Yes, that was correct. I had seen that. That was correct. Yeah, but for those who have not submitted, okay. Yes. So I think that's it for today. The last. Now you can just try it yourself. Okay. So I'll just repeat the plan for the next week for those who joined late. Otherwise, you guys can, those who can leave.